Human mythology includes a wide variety of strange and sometimes monstrous things. Cultures from more northerly latitudes often include distinctly wintry beings among their tales and legends. Examples include Skadi and the other Jotun in Norse mythology, Boreas and Khione from Greece, the Slavic tales of Dead Moroz, and the Yuki-onna of Japan. More modern colloquialisms include terms like Old Man Winter or Jack Frost. While their motives and roles within stories may be quite different, these are all beings of the cold, with affinities for ice and snow. Many are embodiments of winter, and often include a cautionary aspect, as the colder seasons can be quite dangerous for those living in more Arctic latitudes or alpine elevations. Whether or not there is any truth to such myths, there are certainly more mundane creatures that are denizens of the cold. Forms of life that survive freezing temperatures and often feed upon the remains of winter's victims. Strange creatures that sometimes find even the mild warmth of a human touch to be lethal. These are the Cryophiles, also known as Psychrophiles. They may be regarded as a form of extremophile, as they exist near the edge of habitable conditions for conventional life. Other sorts of extremophile include specialists that survive at high temperatures, extremes of acidity or alkalinity, high salinity, or particularly dry conditions. There are quite a few other exotic and difficult environments on Earth, each with their own oddly adapted forms of life, but such details are best saved for other occasions. For now, it is sufficient to focus upon the Cryophiles. These organisms may be loosely defined as having optimal growth temperatures somewhere below 15 degrees centigrade, or roughly 60 degrees Fahrenheit. This might at first seem unimpressive, as 60 degrees would be a slightly chilly spring afternoon in many parts of the world. However, it is important to keep in mind that for typical cryophiles, these cool temperatures are at the upper limit of their tolerances. Most are far more comfortable somewhere around 30 to 40 degrees Fahrenheit, and a number of microbes in particular manage to thrive well below freezing temperatures. For the sake of sanity, I will not attempt to exhaustively review all denizens of colder climes. To begin with, I intend to confine today's investigations mainly to the northern hemisphere. Antarctica is home to a number of remarkable cold-tolerant species, but that continent is perhaps best considered in a video all its own. There are a great many microbes that can survive colder temperatures, and a few that even prefer them. However, I believe it would be more interesting to consider the more complicated multicellular forms of life that are adapted to the cold. Thus, I don't intend to focus upon any bacteria, algae, or other such groups. I also intend to leave aquatic forms alone, at least for the most part. There are some remarkable aquatic species that are adapted to the cold, especially in polar waters, but the number and variety are a bit excessive to take in all at once. Besides this, many of the more extreme cold adaptations are found in land-dwelling species. Furthermore, when I speak of proper cryophiles, I am not talking about any warm-blooded creatures. Though something like a polar bear or a penguin is certainly capable of existing in cold environments, their internal tissues are maintained at a much higher temperature. At the risk of sounding a tad whimsical, such creatures carry a bit of summer inside themselves to survive the winter. For today, I am more interested in proper creatures of winter, species that are cold all the way through, so to speak. I am also not going to focus too deeply upon species that merely survive colder seasons by hibernating through them. There is a great deal of difference between living in the cold and merely waiting it out. That being said, there are a few rather extreme examples of this strategy, and these at least will be worth a look. Within these limitations, our focus will mainly be on lichens, plants, and arthropods, or at least a representative sample of these significant groups. So let us take a closer look at a handful of species that prefer to be left out in the cold. For a physicist, temperature may be regarded as a measure of how rapidly a substance's atoms are moving. A warmer liquid or gas has molecules or atoms moving at higher velocities. A warmer solid has molecules or atoms vibrating with greater energy. Thus, one might think of lower temperatures as a simple slowing down at the molecular level. Incidentally, this is why it is impossible to get colder than absolute zero. This is the temperature at which all motion ceases. To get colder than absolute zero, one would need to come to a complete stop, and then slow down even more. Based upon this, one might think that life in the cold shouldn't be all that troublesome. After all, it is merely a case of everything slowing down. Obviously, in practice, this is not the case. Sufficient cold is quite lethal for most forms of life. Even the specialist cryophiles have their limits, and freezing these hardy organisms below certain temperatures will kill them as well. There are a few significant reasons that cold is so dangerous for living things. First, life as we know it is largely based upon organic molecules dissolved in a water-based solution. Though some species may temporarily dry out and enter a state of suspended animation, water is an unavoidable part of active living organisms. At sufficiently cold temperatures, this inevitably leads to ice. Ice crystals may be pleasant to look at, but they are remarkably destructive when they form inside of living cells. Part of the reason for this is the fact that, unlike nearly every other substance, water expands as it freezes. Since the cytoplasm of cells is based upon water, each living cell contains a significant amount of the stuff. If this water freezes, the immediate result is an expansion of the cell's contents beyond the membrane's ability to properly contain. The force of this expansion is quite formidable. There are many documented cases of trees explosively splitting open during abrupt cold snaps as the sap inside the tree freezes and expands. This is accompanied by a sound that has been likened to a gunshot. Severe though this may be, it is only a part of the problem. Smaller ice crystals are often quite jagged in their overall structure. One would only need to look at a snowflake under a microscope to see this. Imagine a series of tiny blades suddenly appearing inside of a cell, then rapidly growing outward and ripping the various microstructures apart along the way. This is why frostbite is such a concern for humans without adequate heat or insulation. Anecdotes of a person losing a few fingers or toes in this way are unfortunately all too factual. The frozen tissues are essentially destroyed from within at a cellular level. There really isn't any coming back from that, at least for human cells. Still, if a species is able to produce substances that can prevent ice crystals from forming, or even from forming too rapidly or too extensively, this can mean the difference between life and death in a cold environment. Cold-adapted species often have special proteins or other substances in their cells that function as a sort of antifreeze. These substances prevent the formation of ice crystals or limit the extent of their growth, or slow the crystal formation enough for the cell to adapt and not be torn apart in the process. In some cases, an organism might allow its cells to lose a significant amount of water as temperatures drop. By the time the freezing point is reached, there is plenty of room inside these shriveled cells for expanding ice crystals to form without breaking anything. Beyond the problem of expanding ice, there is also the issue of cellular membranes. At normal temperatures, these membranes are essentially fluid in nature, taking the form of a lipid bilayer. As the temperature falls, the membranes might solidify. Physically, one might consider the difference between a thin layer of melted wax and a thin layer of solid wax. A fluid membrane can stretch and bend in response to the forces it encounters. A solidified membrane becomes very brittle and effectively breaks apart under even minor forces. This is understandably rather bad for the cells. In cold-adapted species, the fatty acid chains in their cell membrane lipids tend to be a bit more unsaturated. Functionally, this means that they remain fluid at lower temperatures, allowing proper cellular functions to continue. Incidentally, this is also why fish found in cold water have more unsaturated fats in their bodies compared to warm-blooded mammals and birds, which tend to have more saturated fats. One problem with this different chemistry is these more unsaturated cell membranes may become too fluid at warmer temperatures. This can similarly disrupt cellular structure and function, leading to an untimely demise for the unfortunate creature. Finally, there is the matter of enzymes. Enzymes are proteins that catalyze specific chemical reactions within living creatures. Such catalysts have optimum temperature ranges for their operation. Too hot, and the enzyme unravels and becomes permanently non-functional. Too cold, and the catalysis effectively stops. Cold-adapted organisms tend to have enzymes that operate normally at much lower temperature ranges. One potential issue is they might sometimes unravel with relatively little heat, once again leading to death for the cryophile. There are also a number of structural and behavioral adaptations found in cryophilic species, but these are best addressed along with the specific creatures. With that, it is time to look at a few examples of such forms of life. To begin with, it may be worth considering one of the more tenacious species on the planet. Rusavskia elegans is a variety of lichen that is commonly found growing on exposed rock. It tends to be a vibrant orange or red color, expanding outward along the stone surface in a roughly circular pattern. This overall appearance is reflected in its common name, the elegant sunburst lichen. This species can be found on every continent apart from Australia. While it is not necessarily confined to cold climates, it does appear to prefer them. It is found mainly in Arctic and alpine habitats and is capable of carrying out metabolic activities well below freezing temperatures. It is also one of relatively few lichen species that can be found in Antarctica. At high enough latitudes and high enough altitudes, the lower layers of soil are frozen throughout the year. This permafrost is rather inimical to plant growth, and thus deep root systems aren't really feasible in this sort of environment. The northern atmosphere is similarly inhospitable, with the formation of the Arctic polar vortex every winter. This phenomenon includes high sustained wind speeds, more than enough to topple any tree without a sufficiently deep and extensive root system. Because of these conditions, stunted growth is the rule among the cold-adapted plant species found in the northern tundra. A remarkable example of this phenomenon is the Arctic willow, Salix arctica. This plant grows in tundra and moorland with a circumpolar distribution. That is, it can be found in the northernmost regions of North America, Eurasia, and Greenland. It has the distinction of being the northernmost species of woody plant currently known. Further south, it can also be found growing in mountainous regions at sufficiently high elevations. When one thinks of a willow, a likely mental image would be a tree of some sort or another, perhaps a somewhat small tree growing near the water, maybe something with gracefully arcing branches hanging languidly over a gentle stream or a tranquil lake. The Arctic willow does not look like this. This plant is essentially a creeping shrub that grows close along the ground. No branch reaches more than a few inches upward. The only structures that gain any notable height are the catkins, and even this is only due to the necessity of wind pollination and seed dispersal. While catkins often hang from the branches of other willow species, those of the Arctic willow grow more or less upright, rising from the low, creeping foliage. Despite its humble dimensions, this plant is quite remarkably useful to resident humans in the northern regions. The plant finds use as a form of fuel, a medicine, and even a food source. It is worth noting that certain parts happen to be rich in vitamin C. Still, humans are not the only species to rely upon the Arctic willow. Quite a few birds and mammals feed on this plant, and it is the primary host plant of the Arctic woolly bear moth, Gynophora groenlandica. More specifically, it is the primary food source for the caterpillar of this rather singular species. In all of its life stages, the Arctic woolly bear moth is a rather unassuming little creature. The adult moth is drab and relatively unimpressive. While both males and females have wings, the males are generally the only ones that fly. Their lives are measured in mere weeks as they spend the brief Arctic summer in search of mates and suitable places for laying eggs. They are not known to feed and instead appear to survive on energy stores during this time. The eggs they leave behind hatch before winter's onset, and the caterpillars go to ground as their world freezes over. Unlike the adults and the eggs, the caterpillars of this species are quite resistant to cold, or rather, they are resistant to dying due to freezing solid. Typically, they weave a diffuse net of silk about themselves before allowing the cold to take them. The caterpillar tissues contain significant amounts of glycerol and other substances that prevent the rapid and uncontrolled formation of ice crystals. As winter closes in, the little creatures enter hibernation. After roughly 10 months or so, the fleeting summer weather returns, and the caterpillars emerge from their frozen sleep. They spend their time either feeding on available vegetation or basking on rocks to warm themselves enough for digestive processes to actually be feasible. As the warm weather ebbs, they return to hibernation, once again wrapping themselves in thin veils of silk. This cycle repeats for at least 7 years, and possibly longer, depending upon the precise conditions. As the tiny caterpillars slowly grow, they take on appearances appropriate to a woolly bear. These particular creatures are lacking the showy coloration of some of their cousins. Instead, their dense covering of hairs is a tawny, almost rusty sort of hue. These hairs are thick enough to function as a proper layer of insulation, and there are only a few other sorts of caterpillar that could rival the degree of fuzziness. The overall appearance is perhaps reminiscent of a rather frayed, rust-stained bottle brush. Not the most flattering comparison, but it is at least functional. There are a number of other surprising insect groups that also embrace the cold. One of the more famous is Belgica antarctica, a variety of wingless midge. It has the distinction of being one of the only native terrestrial arthropods found on the southernmost continent. Still, our focus here is on more northerly latitudes. There is another group of wingless flies that have a penchant for clambering about on the snow. These so-called snow flies are in the genus Chionia, and they are a wingless variety of crane fly adapted for the cold. Incidentally, the genus name pretty much translates into snow, which is perhaps to be expected. While these flies are lacking in wings, they have long legs much like those of their immediate relatives. They are often found in wooded areas during winter and in mountainous regions. As the name suggests, they are adapted to walk across snowfields with reasonable success. Still, there are a few minor issues as these gangly creatures clamber about in the cold. Their bodies are relatively dark, particularly against a background of snow. It is likely that this coloration might afford them at least a slight thermal advantage on sunny winter days. After all, dark objects absorb sunlight more readily and tend to heat up more extensively under sunny conditions. Like the Arctic woolly bear moths, these snowflies do not feed as adults, and they spend most of their lives as larvae. I would suspect that the adults emerge in winter to avoid predation. There aren't all that many other creatures to be found out on the snow, after all. It is even fairly dangerous for the snowflies, as it turns out. While they do have some degree of cold tolerance, their legs are prone to freezing and adhering to the snow in the process. It is something like the ill-advised dare of placing one's tongue against a metal flagpole during the winter. Don't do this, by the way. It is an effective method of losing a part of one's tongue. As for the snowfly, a frozen foot presents a similarly serious issue. Worse perhaps as ice crystals begin to spread upward through the leg. The solution to this problem is effective, if somewhat extreme. The leg is sacrificed as the fly severs it before the ice crystals can reach its body. Apparently, it is not uncommon to see one of these flies walking along on 3 or 4 legs rather than the proper 6. Despite the severity of this disfigurement, it is not a great loss for the little creatures. After all, their adult lifespans are limited to only a couple of months. Even this is fairly long for insect species that don't feed as adults. Most likely, the low temperatures prolong their lives at least a little. Another similar insect group is the snow scorpion flies in the family Boreae. This family name refers to a boreal or northern habitat. They are found throughout the more northern latitudes as well as suitably mountainous regions. Their common name is derived from a couple of features. The connection to snow should be obvious enough. As for the affinity with scorpions, that is more of a reference to scorpion flies in general, also known as the order Mycoptera. By a curious quirk, the males of many Mycoptera species have a structure at the end of their abdomens that looks a lot like a scorpion stinger. However, this is not a weapon and it is not at all venomous. Rather, it is an organ that is more concerned with producing the next generation of scorpion flies. I trust that this is a sufficient explanation. Another odd quirk of the scorpion flies is their remarkably long faces. The mouth parts aren't particularly modified for piercing or sucking, but they are stretched out into surprisingly pointed snouts. For an amateur entomologist, this characteristic head shape is a quick means of distinguishing a typical female scorpion fly from a crane fly. Returning to the Boreae, these particular insects are wingless like the snowflies. At most, there are remnants of wings reduced to little more than bristles. A typical species within this group would be Boreas hyemalis. As with the family name, the genus name here refers to the north. As for the species name, it roughly translates into winter. So yes, there is an insect that is effectively named Northern Winter for all intents and purposes. Like others in their family, these insects are relatively small, maybe half a centimeter in length at most. Unlike the other insects mentioned thus far, the adults of this species eat food and are relatively long-lived. Both the adults and their larvae feed mainly on mosses and spend much of their time on moss beds. Most of their time on the snow is spent walking between various feeding grounds. Of course, they do have a degree of cold tolerance, and their dark coloration helps them to absorb solar radiation to help stave off the cold. In addition, it is worth noting that snow is not especially conductive so far as heat is concerned. The small size of these insects also keeps them close enough to the ground to avoid any significant air movement, as there is a thin boundary layer of relatively still air over any solid surface. Since they only traverse the snow on their way between moss beds, they aren't nearly so prone to losing a leg as the distantly related snowflies. As the Boreads are sometimes known to hop as well as walk, they are sometimes called snow fleas. This is a bit confusing as they are not fleas. Granted, scorpion flies are among the closest known relatives to actual fleas, but the groups are quite distinct from one another. To make things all the more troublesome, there is another insect group that is more commonly known as snow fleas. Incidentally, these are not actually fleas either. The collembolans, or springtails, are a diverse group of wingless hexapods known for their small size and the presence of a furcula. This furcula is an appendage that catapults a typical collembolan a considerable distance as a means of escaping from would-be predators. Collembolans are commonly found in soil and moss and a number of other places. It should be no great surprise that there are cold-tolerant varieties that are sometimes found on snow. Hypogastrura navicola is a collembolan species with a dark blue coloration. The species name roughly translates into snow dweller, and this is quite apt. Like many other cold-tolerant species, the cells in these arthropods contain special proteins that limit ice crystal formation and act as a natural antifreeze. This is just as well, as they lack the long, spindly legs of the snowflies and cannot feasibly resort to amputation in the event of a frozen foot. As is the case with other collembolans, these dark little springtails are quite tiny. However, they can sometimes be found in large groups on certain snowfields. The overall effect at a distance is an unusual sort of dark blue stain on the snow. A closer look reveals this patch of color is made up of thousands of tiny little specks that are slowly moving about. Thus far, the organisms we've looked at are specialized species with a number of close relatives that are not especially adapted to the cold. Many lichens are tropical. Willows, while generally more temperate, mostly grow in warmer places than exposed tundra. Midges, crane flies, scorpion flies, and collembolans can all be found in warmer climes as well. There is one odd little insect order that consists entirely of cold specialists, however. These are the Grylloblattodia, also known as ice crawlers. The only family within this order is the Grylloblattidae. Both the order and family name roughly translate into cricket cockroach. The name is easy enough to understand given the appearance of these wingless creatures. At a glance, a typical ice crawler is a yellowish-brown insect that looks like something between a cricket and a cockroach. The taxonomic cohort known as Polyneoptera includes such creatures as cockroaches, termites, mantids, grasshoppers, crickets, earwigs, stoneflies, stick insects, and the ice crawlers. Despite the name, these insects actually tend to live in leaf litter and under rocks. However, they are mainly found at the edges of glaciers or in ice caves, particularly on high mountains. They are definitely cold adapted, as their preferred temperature typically ranges between just above freezing and perhaps 40 degrees Fahrenheit. They forage for food at night and often subsist on the remains of insects that have succumbed to the cold. When temperatures drop below freezing, the ice crawlers tend to burrow beneath the snow and stay close to the soil. Somewhat ironically, these insects are not able to survive being frozen solid, so they avoid sub-zero temperatures. Most species of Grylloblattids are found in western North America, Russia, and East Asia. However, their actual ranges are relatively limited as they are confined to high elevations. Actual freezing may be a problem for these creatures, but warmer temperatures are also rather dangerous. Above roughly 50 degrees Fahrenheit, they begin to succumb to the blistering heat. Even holding a Grylloblattid in the palm of your hand for too long will give the poor little creature a lethal case of heat stroke. Thus they remain confined to their mountainous homes, while the surrounding lowlands swelter in the blazing inferno of what we would think of as room temperature. In the end, it is much the same for any specialist. Adaptations to the cold tend to make one more susceptible to heat. Adaptations to survive in hotter climates tend to make one more likely to perish in the cold. An especially fast runner usually has weak defenses. An armored defense will limit movement. Feeding on a plant most creatures avoid may give you access to a private food supply, but other vegetation is soon off the menu. Every specialization involves a trade-off of one sort or another. The specialist cryophiles can survive in some of the harshest and most extreme environments on the planet. However, place them in conditions that we might find comfortable, and they would soon be outcompeted by other species if they didn't simply perish on the spot. Even so, such adaptations are a part of the variety of living things, and such variety is an essential part of life. Thank you for listening, and I hope you have enjoyed today's little foray into the unknown. If you are still curious and wish to venture a little further, here are a few things you might consider looking into. If you found this video enjoyable, do feel free to leave a like. If you believe others might enjoy it, by all means, share. If you wish to see more of this channel, a subscription should prove quite helpful. Until next time.